Okay, we're going to move on to number 90. Number 90 states a buffer solution is prepared from an equal volumes of 0.2 molar acetic acid and 0.6 molar sodium acetate. Use 1.8 times 10 to the minus 5 as the Ka for acetic acid. What is the pH? Is the solution acidic? And if you add 3 milliliters of 0.034 molar hydrochloric acid, what is the new pH? If it's added to 200 milliliters or 2.2 liters of the original buffer. Okay, so first of all, the equation we're dealing with here is C2H3O2 acetic acid plus water goes to form H3O ions, hydronium ions, plus the acetic acid or acetate. And the Ka, which is 1.8 times 10 to the minus 5, is equal to the concentration of hydrogen ions times the concentration of acetate ions divided by the concentration of acetic acid. So if we assume that we take half a liter of this and a half a liter of this, we have the following amounts. If we have a 0.2 of a molar solution and multiply that by half a liter, we end up with 1 mole, 1/10 of a mole of acetic acid. We take 0.6 molar times a half a liter, and this just makes the math easy, that this assumption of volume. So it's this molar. And the total here is 1 liter, so the molarity for acetic acid is 0.1 molar, and the molarity for acetate is 0.3 molar. And with that, we can now make our little box. And in that box, we're going to put 1/10 molar acetic acid, no hydrogen ions, and 3/10 molar acetate. We're going to subtract X from the reactant side. So at the end, we have 0.1 minus X. We're going to add X to represent the acid that's produced, and we're going to add a similar X to the acetate that's produced. And so this will be 0.3 plus X. And then we can substitute these values in here and say that X times 0.3 plus X divided by 0.1 minus X is equal to 1.8 times 10 to the minus 5. And so X here is going to equal, if we assume these are significantly smaller than this, we get 3X is equal to that. So if we divide 3 into that, we get 6 times 10 to the minus 6. And if we put that in our pH formula, we get a pH of 5.22. Now, the second part of the question says we're going to add 3 milliliters or 0.003 liters of 0.034 molar HCl. Now we have to assume, well, first of all, the amount of this is going to be multiplying the volume times the molarity. Will tell us the moles of this, and that's 1.02 times 10 to the minus 4 moles of hydrogen, or H3O. And this amount will be subtracted from, or will be added to this, because when you add here, it shifts it this way. It subtracts this amount from this and adds it to this. So if we take 0.1 plus 1.02 times 10 to the minus 4, we get 0.1001 moles of HAC, which is HC2H3O2. And if we take 0.30 minus 1.02 times 10 to the minus 4, we get 0.2999 moles of the acetate ion. The total volume now is going to be 1 liter plus 0.003, or 1.003 liters. So the new concentration for acetic acid, it's now going to be this new moles divided by the new volume, and that's going to give you 0.0988 molar. And the new for this is now going to give you 0.299 divided by 1.003. It's going to be 0.2990 molar. And if we do the same calculation we did up here, except substituting these amounts, we're going to get X times, now this 0.299 minus X, or plus X, divided by 0.098998, excuse me, this is a 9 here, sorry about that, minus X, and that's going to equal 1.8 times 10 to the minus 5. And if we do the math here, again, assuming these two approach 0, then 6.008 times 10 to the minus 6 is equal to X, and that pH is now 5.221. So adding this concentrated acid did not change the pH significantly. And that's how buffers work, is that you can add strong acid to a system and you don't end up causing a significant shift in pH. So let's look now at 94. And I'm not going to do all of these. I'm just going to do the first 3, and you can do the last 2 once I do the first 3. So if we just use A for barbiturate acid, so HA plus water goes to form hydronium ion plus the barbiturate anion, and we're told it's 9.8 times 10 to the minus 5, and this is going to equal the concentration of HA divided by concentration of A times the concentration of H3O plus. So in the first situation, we have a 0.1 molar solution. So if we do our box, we have 0.1, X, and X. Or excuse me, 0 and 0. The change is minus X here, plus X here, plus X here. So you have 0.1 minus X, X, and X. So that 0.1 minus X divided by X squared, I got this backwards, I'm sorry. This is going to be A, got it upside down. What a goober. So let me get this right here. So now this is going to be X squared over 0.1 minus X. We assume that X approaches, and so if you multiply 0.1 times this number, you get X squared is going to equal 9.8 times 10 to the minus 6. And the square root of that is 3.13 times 10 to the minus 3. So the pH, the initial pH, is 2.50. So now we're going to add hydroxide. And how much are we adding? We are adding the volume, which is 0.02 or 20 milliliters, and we're adding 0.1 normal or 0.1 molar. And so the total is 0.002 moles of hydroxide added. Now, when you add 0.02 hydroxide, this goes away, so this shifts this way. So you assume it's like taking that much of HA out. So if we do that, that means the HA amount is now 0.04, which is 0.04 times, and then minus 0.02. And that's going to be equal to, or 0.02, excuse me, and 0.04, sorry about that. And so that's going to be 0.002 moles of this. I kind of stumbled over that a little bit, so let me go back, make sure you got it. The original HA is going to be, now you're you're adding 20 milliliters of this to 40 milliliters of this. So the original HA is 0.04 times, and this is originally 0.1 molar, 0.1, so you end up with 0.004 moles of this originally. And what's left after you've added the hydroxide is you subtract from that, and so that gives you this. At the same time, this has the effect of adding, remember we're taking this away, so it's shifting this way, so you're adding 0.0202 of A minus. And so you have, let me take these out because it's not really concentration yet. It's just the amount. So it's not confusing. So we have this much of this. When you add this to it, the shift causes this amount to decrease by this. So now you have this much HA and this much A. The total volume is 20 mils plus 40, or 60 mils, which is the same as 0.06 liters. So now the concentration of of HA, concentration of HA is going to equal this amount, 0.002 divided by the total volume, 0.06. So the concentration is now 0.333 molar. And A is the same calculation, and it's this, so it's 0.002 divided by 0.06. And so it's also going to be 0.333 molar. So now these are your new concentrations after the addition of hydroxide. So that's what you put in up here. So if you do your table, you have 0.0333, 0, and 0.0333. You're going to add X on this side. You're going to add X here and subtract X here. So you have 0.0333 minus X, X, and 0.033 plus X. So when you do your formula here, it's going to be X times 0.0333 plus X divided by 0.0333 minus X. Again, if you assume these are small compared to this, you're left with this, and these cancel each other out, and so this is equal to 9.8 times 10 to the minus 5, and so X is now equal to 9.8 times 10 to the minus 5. So that's the hydrogen concentration now. And so your pH is now the negative log of this, which is 4.01. So by adding 20 milliliters of hydroxide to this solution, you've raised the pH from 2.5 to 4.01. I'm going to do one more, hopefully without stumbling over my words. So let's start right with this, because that's the next step, is you're now going to add 39 milliliters. So how much hydroxide are you adding? Well, you're adding 0.039 times 0.1. So it's now 0.0039 moles of this, of hydroxide. So the HA, which was originally this amount, you're going to now subtract this, so it's 0.004 minus 0.0039, and that's going to leave you 0.0001 of HA. And A is, you're adding this, so it's 0.0039. The new volume is 40 plus 39, or 79 milliliters, or 0.079 liters. So the concentration of HA is going to be 0.0001 divided by 0.079, and that is going to equal 0.00127 molar. The concentration of A is going to be 0.0039 divided by 0.079, and so now that's going to be 0.0494 molar. So these are your new concentrations. You put those in this again. So instead of this, you're going to have in the denominator, I'm going to put it here. Well, let's move it up here. But I want you to be able to see this. So here, you're going to now, instead of this factor, you're going to have this number minus x. So it's going to be 0.00127 minus x. And on the numerator, you're going to have x for the hydrogen ion concentration, and you're going to have this 0.0494 plus x in the numerator, and this is going to equal 5 or 9.8 times 10 to the minus 5. If you, again, assume these are small, you end up with x times 0.0494 divided by 0.00127 equals 9.8 times 10 to the minus 5. And that, in that situation, x is now going to equal 2.52 times 10 to the minus 6. And the pH is now going to be 5.6. 0. So you've gone from 2.5 up here to 4.01 to here to 5.6 here. And I'll let you do the rest. You'll notice, as with the next addition, with the first addition of 20 milliliters, you went from 2.5 to 4, so you went up 1.5. You added 19, and you went up 1.6. As you can see, the next one is 40, and with 40, you'll see that the pH goes up even more, and that's what happens as you get close to the inflection point. So anyway, I'll let you do those last two on your own, and if you have any questions, I can work through those with you.